Hello, this is Team 2. We chose to do image classification for human detection. On this project is myself, Jonathan Long.
I'm Faisal.
Hello, everyone. My name is Rene Ortiz.
All right, thank you. Let's go to the next. All right. So our effort here was to develop an algorithm primarily to perform human detection and the presence of humans within the images. So to do this, we use different convolutional neural networks, and I'll let Rene go ahead and talk about the model that he evaluated.
Yes, I read about AlexNet breakthrough during the 2012 ImageNet competition and how it's still relevant until today, since convolutional neural networks are commonly used for large-scale image classification problems. I decided to base my side of the project on this model.
All right, and I chose VGG16 from the Visual Geometry group from University of Oxford. This model is known for simple image classification tasks, and so I chose to go with this model.
The model that I chose was SVC, which stands for Support Vector Classification. It's a supervised machine learning algorithm used for majority of simple classification tasks. The reason why I chose a regression model like SVC was because it's not a neural network model, so therefore it's more lightweight. It stores less layers, and it runs a little bit lighter. So that's, and then we can explore more as to why I chose this later on in the slides.
The model I selected for this project is AlexNet. It is a breakthrough model in deep learning, especially in the application of convolutional neural networks to large-scale image classification problems. It highlights the power of deep learning in real-world tasks. The success of AlexNet in the ImageNet competition in 2012 marked a significant milestone in the field of deep learning and computer vision, demonstrating the power of deep convolutional neural networks for image classification tasks. Its architecture and training techniques are still relevant today and continue to influence other models and AI advancements in computer vision. AlexNet is composed of 8 layers, which will be explained in the next slide. Also, AlexNet uses ReLU function, which allows us to learn complex patterns and features from the input data. Another key element is data augmentation with techniques such as cropping, flipping, and altering RGB intensities to artificially expand the training dataset, improving generalization. AlexNet convolutional layers extract hierarchical features from the input image. Max pooling layers are used to downsample feature maps, reducing the image dimensions and simplifying the computational load. The fully connected layers process the extracted features to classify the input image into one of the thousands of ImageNet classes. If we look at these diagrams, we can see that the model does max pooling at the image input after the first layer, and every single conv layer increases the number of features maps while decreasing the resolution with max pooling. These two diagrams are equal. I just find this one easier to visualize. We can see that the first layer takes the 227 by 227 by 3 image size, and then it applies max pooling after it. For on layer number 2, it gets an input size of 27 by 27 by 96 features. And we can see here how each output increases the features for each next layer. The last 3 layers are fully connected, and FC1, FC2, and FC3 are responsible for increasingly transforming and refining the learned features from the convolutional layers into a format that is suitable for classification. FC1 and FC2 perform feature abstraction and ReLU activation, while F3 computes the final class probabilities using softmax activation, enabling the network to make accurate predictions on the image dataset. So fundamentally, the model consists of an image input of 227 by 227, 5 convolutional layers, 2 fully connected layers, and 1 output softmax layer. Moving into the data set that I used, this data set was downloaded from kaggle.com. It has 921 images split into 2 folders, one with images with humans in it or people, and the other one without humans or without people. And on this plot, we can see the distribution of those 2 folders. Images with humans are a little bit over 500 images, and images without humans are close to 400. All of these images include images from indoors and outdoors, which is relevant to our classification tasks. During the initial implementation of my AlexNet model, I loaded the model with predefined weights. And I found that, well, pre-trained weights from AlexNet can provide a valuable starting point for transfer learning. The effectiveness outside the context of ImageNet dataset and related tasks can be limited by domain-specific features, overfitting, and dataset characteristics. Here on the screenshot, it shows I used 10 epochs, and an epoch refers to 1 complete cycle through the entire training dataset. With predefined weights, the test accuracy never went above 50%. I had probably in average, well, not in average, but in every single epoch, 47.57% accuracy, which is quite low. To get a better performance, I added 2 functions for the training process, and those 2 were cross entropy loss and SGD optimization. Using specific loss functions in cross entropy loss and algorithms like SGD offer several benefits in terms of the training stability, conversion speed, and overall performance. We can see here that the loss from each train was decreasing as the epochs were processed. And we can see also on the test accuracy how after the first epoch, all of the rest had a higher accuracy of 90%. So in average, I think it was above 92%, which is a lot of improvement from our predefined weights originally tested. Once with this accuracy, we can see that the confusion metrics showing 103 images that were properly classified with humans and 6 were misclassified with no humans when actually there was. And also for the images for non-humans, we had 7 that were misclassified and 69 that were classified properly. This is using the standard 80-20 ratio of our dataset. That is 80% for training, 20% for testing. Once that the model was built, I did some manual testing for random pictures, and those were classified properly. Here on the right, we have 3 images with humans, and they were processed by the model, AlexNet, and they were properly classified with humans. You can see the 3 of them have humans in them, and the one without is properly classified without human. So that shows how effective this model it is for image classification.
I chose to select the VGG16 model, which was first proposed by the Visual Geometry Group of University of Oxford's Department of Science of Engineering Group. This was proposed in the paper Very Deep Convolutional Networks for Large-Scale Image Recognition, published in 2014. So the model is pre-trained on ImageNet data for generalizability and performs well for large-scale image recognition and classification. All right, so hopping into the architecture, we see that the model takes an effective approach. It decreases the kernel size and has a lot of convolutional layers. Here we have 13 convolutional layers, filter size of 3 by 3 with a stride of 1, 5 max pooling layers with strides of 2, and 3 dense, fully connected layers, with the last layer being a soft max. Okay. All right, the model, let's talk about optimization and loss function. The model was optimized using the Atom optimizer, or the adaptive moment estimation. Here we see theta. I've listed it mathematically. We see that theta represents the model parameters. And the Atom optimizer is an adaptive learning algorithm. It's suitable for training deep neural networks. And the loss function that we've chosen is the binary cross entropy loss function, or the log loss function. It measures the difference between probability distribution and the true distribution. And it also heavily penalizes the model when making predictions that are confidently wrong. All right. Two great options for binary classification problem. Here, training the model, we trained the model on 10 epochs and a batch of 16, which resulted in a test accuracy rate of 85.4. So after consideration, I thought to fine-tune the model, or partially fine-tune the model, after doing some research, such as looking at research from the university that I've listed, University of Johannesburg, classification and detection. So the VGG16 model has been known to notably have increase in effectiveness when fine-tuned. And so fine-tuning was done by peeling back the top layer, unfreezing it, and allowing the model to take advantage of some of the pre-trained data from ImageNet. All right. So some things to take away with, I would say the increase in loss in Epoch 2 with relatively small batch size. I didn't expect any smooth curve or any smooth curve estimation. Each batch provides a noisy estimate of the gradient. So as we see here in Epoch 2, we see a decrease in accuracy and an increase in loss. So just knowing the scale of the data, it's probably undistinguishable when we're faced with assessing all of the epochs, especially if we added more epochs. But just for visualization, maybe there's some statistical reasoning that I could have done and could do in the future to make that more legible. Next steps will be to, number one, definitely reevaluate the data set. I know that we're working with around 920 images. I know that's under 1,000 instances. And so if there was maybe we can combine different data sets and add to the data set to really get a better response or more accurate prediction. And the number two thing that I want to walk away with is human tracking. I know that my group, Team 2, we decided to take on the task of human tracking. However, we ended up with human detection. So we built models that were kind of catered towards assessing if there was a human in the image or not, but not necessarily assessing the coordinates of that image. It's something that we talk about in the conclusion as far as trying to apply this model with use in using heat maps. So also, yeah, so some models that would have worked for assessing human coordinates within the image, um, that would involve convolutional networks with recurrent connections and doing further research. Hourglass network, mask R, CNN. You only look once. So some of these models may have been better suited for the human tracking task.
The model that I chose to help with classification of humans and non-humans in an image was SVC, which stands for Support Vector Classification. SVC is a supervised machine learning algorithm. It's a regression model that is used for majority of simple classification tasks. The reason I went with a regression model instead of a neural network model was mainly because it's a lightweight model because it doesn't have a lot of layers. So I figured it would be more effective to run this on each frame in the image of a video. So therefore, choosing a lightweight model would be better. So that's why I chose support vector classification. So to make it work optimally, what I did was I used a bunch of tuning parameters with the help of grid search CV, which is offered by the scikit-learn library in Python, where you could essentially provide it a range of gamma variables and also a C variable, which essentially it will automatically run between the increments that you provide and best find what parameter are best for your data set. So after running the grid search CV for SVC, as you can see, that the best gamma value and C value that turned out to be was gamma being 1 and gamma being 0.001 and C being 1, which outputted our accuracy to be about 0.636. So about 64% accuracy. Of course, this is not the best. The accuracy is about, I'd say, moderate at best. And the reason is because it's not a neural network model. Neural network models work great for images because they're able to store features in the layers themselves. And they're a lot quicker at learning those features than a regression model, because the regression models are not designed that way. They're simple regression models that they're easily overfit or underfit for different data sets. So how can we make it better or perform it or make it perform like a neural network model? And the way we can do that is to essentially do what neural networks do, but do it before we actually train the model. So what we would do is extract the features from the images beforehand. So essentially we would use algorithms like HOG feature extraction, which essentially extracts the edges in an image, or CNN, which would extract the colors or contour and all that kind of stuff, so that the model doesn't have to run and do it. But you do it beforehand, and you let the model, the SVC model, train on those extracted features from the images. So that would potentially be a better accuracy, or higher accuracy, more closely in tune with a neural network accuracy.
In conclusion, we can see here on this slide the final 3 accuracies for the 3 models that we researched. From my side of things, AlexNet got a 92.97% accuracy, and that is after optimization, which with a few additional steps, we got a higher accuracy than expected.
All right. And likewise for me, after fine-tuning my VGG16 model, I came out with the accuracy of 91.89, which led to a model that fit the standards for the project at hand.
And for support vector classification, the best accuracy that I was able to receive was 63.3%. It's not as high as the other neural network-based architectures, as my peers described, because it's a regression model. Next slide. Our goal for this project was to essentially be able to determine where a human is in an image or not. And the data set that we used was derived from CCTV footage images, which either said this image has a human in it or not. So when we actually went ahead and trained our model and kind of we're able to look at the heat map that derived from the model output, we're able to see that it doesn't necessarily highlight the humans in the image. Instead, it highlights the area where the humans would be around. So, for example, in this case, you can see the heat map is essentially lighting up for areas where human are, but it's not exactly pinpointing where the human is. And if we try this on another image, next slide, we could see the same thing here. It's not pinpointing where exactly the human is. It's just highlighting, or the heat map is lighting up for the area around it. Just like how we trained on data set images where where the area around the human. So next slide. A potential future optimization, what we could do is essentially train it in a way that pinpoints exactly where a human is in the image. So on the left is what data set we used, right? So we either had images where there was a human in it, or there was an image where there was no human in it. And that's kind of the result we got by the model predictions. What we could have done instead was use data set, or a potential data set like the one on the right side, where essentially it gives you an image and a coordinate kind of for where a human could be. In this case, it's a dog, bicycle, and a truck. But in our use case, it would be essentially a coordinate of where exactly the human would be. That would essentially give us an exact position of the model output that we could essentially go ahead and draw either a box around or do some other thing with it. So yeah, that was our presentation. Thank you for your time.